Good morning, organic chemistry, and welcome back to Unit 3. Now, this is going to be our last section of reactions in our Unit 3. So if you're watching your videos, you don't want to watch this one first. Okay, this is our series, our Sn1 E1s. I prefer if you watch these last. So you want to definitely watch your radical halogenation first, and then your Sn2, then your E2, and then we're going to watch this Sn1 E1 last. So if you haven't watched those, maybe stop this one and go watch those first. So fun. All right, I've chosen to combine these two. Our Sn2 and our E2 had very similar mechanisms. Our Sn1 and E1 do as well. And we noticed in our Sn2, E2 videos, they are in competition. They compete with each other. So do Sn1, E1. So I'm not a big fan of separating them. Let's just put them together. I went ahead and included some links for this one. We've got several links that you can use along with your videos. And also with this video, I've included our little handouts that we've seen in our Sn2, E2, because I'm going to refer back and use those also. So I kind of shrunk this one. We're not going to use it as much, but I still wanted to start with that. Okay, so where are we so far? We are in the middle of learning 5 new reactions for Unit 3. I love it. And this is our last 2 reactions in that unit. We saved the best for last. Isn't that fun? So we learned in our Sn2 and in our E2 that we've got a nice competition. And we learned that the Sn stands for substitution of a nucleophile, and the 2 stands for second order. And that second order means a collision. Now, in today's set of videos, our mechanism isn't at all going to be the same. When we put the 1 in, what does your gut tell you? We are now switching to a first order mechanism. That is not a collision. In fact, that is a decomposition in our rate determining step. And so what's awesome is that you should not mix and match. Your Sn2 and your Sn1 will have 2 completely different mechanisms. And this is actually good news. So what is an Sn1 and an E1? Well, let's go back to our Sn2 examples. If I were to take an electrophile that was primary versus secondary versus tertiary, how did I spot in Sn1? I had a really good nucleophile. So what if we had something like cyanide, and then a really good solvent like DMF? Okay, now our reaction conditions told us Sn2. We had a nice leaving group. Let's label. We had a leaving group. We had a nucleophile, we had a solvent, and then that meant that our leaving group right here was attached to our electrophile. Remember our 4 things. And now our electrophile, if it was primary, we knew this reaction worked awesome. And we substituted our nucleophile for our leaving group. And then we worked our way into our electrophile as secondary, and that reaction was good. It worked. It was slower. That's why we started to get a competition, but it did work. Okay. And then by the time we got to tertiary in our electrophile, nope, because that Sn2 had to have a collision, and our tertiary literally just didn't let that happen. That was nice and blocked. So what we're doing is kind of working our way through our electrophiles and figuring out which reactions work and don't work. So what's awesome is that even though an Sn2 does not work in substituting your nucleophile, it turns out our Sn1 does. So let's actually start our Sn1 with a nice tertiary electrophile. In fact, we're going to see that Sn1 and Sn2 are opposite, and that their Sn1, this works awesome. Now we're going to change up our conditions, and watch this. What? All right, so I want to go and label everything. That's what we've been trained to do. We have our leaving group. We have our electrophile. But son of a motherless goat, we only have a solvent or a nucleophile. We only have one thing there. It turns out for an Sn1, E1, your nucleophile is your solvent. Okay, this is big. This is why I kept the list in here. Okay, your nucleophile is your solvent. So how does that work then? How can a nucleophile be your solvent? Well, the first thing we notice is that they are neutral, but they have lone pair. Remember, what makes a good base or nucleophile? You have to have available electrons. So I brought in our solvents list again. Not every solvent is created equal. Your solvent for an Sn1, oops, that's a little too fluffy. Sn1, E1, your solvent has to be polar and have lone pair. So how do we read our table and figure that out? Well, here's some nice polar solvents. And look, every single one of these has an oxygen with a lone pair. So that works awesome. Okay, those are going to be perfect. So anything in that range that has a nice lone pair would make a really good solvent and a nucleophile. I'm going to go ahead and include a couple more just for fun. Sulfurs can work, okay, but mostly we're going to have alcohols, waters, and acetic acids. Olivia, can you get that? I may have to pause because I've got it. I'm making a video. Sorry, y'all. Video's at home. Okay, so if we're using a nice solvent with lone pair, let's talk numbers for a second. It means we're going to have just millions and billions of those floating around for every one of your electrophile. Okay, so let's go ahead and scroll down and let's write out how this works and why we care. Okay, so the first thing that we noticed was, all right, hang on a second. You have a leaving group on a tertiary electrophile. And yet we still substituted there. How in the world does that happen? And we don't even have anything negative. We do have available lone pair in our solvent. And it turns out your solvent then ended up substituted in your product. Okay, fascinating. All right, so our mechanism is actually completely different for this reaction to happen, and it does happen in a competition with the E. So let's tackle both of them. I will say that our Sn is going to be major and our E is going to be minor in this process. Let's draw our mechanism. Let's tackle it. Okay, now first order means that you have a decomposition. Your tertiary electrophile, that is your rate determining step, it has to decompose. So literally, your leaving group leaves first. All right, now that's an interesting change of events. Okay, now I'm showing literally the decomposition of that electrophile. That has to happen first. Now this is really important that that happens first, and it's actually pretty hard to do. So these reactions, you actually need to add heat and a lot of time, and it kind of sucks. All right, so as this happens though, we're left with our bromine or our bromide as our leaving group. But then what happens to our electrophile? You just stripped electrons away from a carbon and left a positive on that carbon. That is called a carbocation. And what's awesome about a carbocation is, let's hang on a second and let's think about our definition of an acid and as an electrophile. Aren't we looking for available space? Absolutely. Your electrophile just got a boost of steroids. We have a good electrophile here. We have a super electrophile here as a carbocation. And also what changes is its shape in space. You went from sp3 to sp2. That sucker's flat. So now you've got a flat, big, empty space on your carbon. So as soon as you leave that or lose your leaving group, you have just made a super electrophile. This is why you can have a crappy nucleophile. In our Sn2, our nucleophiles were negative and small. They were very reactive. We don't have that in this case. In fact, we have water. Water has available electrons, but they're not negative. It's not nearly as reactive, but we have two things going for us. We have a super electrophile, and it's like Vegas, you have just stacked the decks in your favor because you've got billions of these floating around just waiting to smack into and fill in that space. So then in our mechanism is just a little bit longer than our Sn2. Our water then can fill in that carbocation. Okay, but now we've got a charge on that substrate. We've got a charge on that oxygen. Why? Because you're sharing a lone pair that you're not used to sharing. Water was nice and neutral, and now you're sharing that lone pair. So we're not done. You have a charged species. Your mechanism isn't done until you're nice and neutral. I am going to use and break all kinds of pKa rules, but I want to show you the byproduct. So you have floating in solution water and Br minus. Between the two of them, water is the better base. All right, so this is likely going to happen with water, but I'm going to break the rules and show you that our HBr is a byproduct in this reaction. So what do we actually make out of our Sn1 mechanism? We end up substituting that water. We substitute our nucleophile, which also happens to be our solvent. Okay, you give that lone pair back to oxygen. This is a nice acid-base reaction. And then we form, as one of our byproducts, HBr. And then what is left behind? That's it. So we just made an alcohol and a very strong acid, HBr. Now we know from pKa's wise that you likely are going to have this in your solution as well, so you're going to have to treat that with a little bit of base in your SEP funnel if you're doing this in the lab. So we just made an alcohol. Now, could we shortcut that mechanism? Absolutely not. It is literally telling you stepwise what has to happen in this process. Your electrophile falls apart. Your solvent fills in that space. And then you need to do some acid base in order to relieve that charge. We don't end a mechanism with an overall charge on our product. So this literally has to be all of these steps. Okay, but wait a second, I told you there's a competition. So how do you get the E product then? Well, we are going to start this whole process in the exact same place. Let's lose our leaving group. Now here is where an Sn1 and an E1 always go together. You have just made a very reactive carbocation. Okay, water is pretty stable. So, and you've got 1 million of them floating around. It could also bump into, wait for it, a beta hydrogen. It's literally a competition. Do you fill in the carbocation or do you bump into the hydrogen? And so in this case, you also can make the alkene. And then what is your byproduct? Our byproduct is that H3O plus, Br minus, but isn't that actually water and HBr? It is. So this would be our E1, and this would be our Sn1. They usually come together. Now, if you were to do this reaction in the lab, you would likely make the majority alcohol and a minor E1 product. You'll always make them both, but you can skew it. Now, in real life lab work, these go back and forth in equilibrium, so it is possible to do some Le Chatelier principle here. If you really want the E1, you heat it for longer and you do a distillation. If you really want the Sn1, you really treat that a little bit slower, a little bit colder, and you try not to remove any of the alcohol. So there are different ways to skew it. We won't get that deep. I will let us use this in synthesis, and we will make the Sn1 as our major product. After all, our E1 product, we could make that in a way better way. So I will let us just use that. So then how does this even work? So you'll notice that we have a carbocation. So why did our tertiary work better for this reaction? Remember, we had no Sn2 here, but yes to an Sn1. Why? Because it turns out that carbocations and radicals follow the exact same stability. So our tertiary, the more stuff around it, the more better. Not an English video. So if we're forming that carbocation, this reaction works pretty well on tertiary. It works okay on secondary and not at all on primary. So in fact, Sn2, E2 and Sn1, E1 are kind of the exact opposite. So if I were to take a secondary carbocation and form that, could I form a secondary carbocation? Yes. So what would this process look like? Again, exact same mechanism. You have to lose your leaving group first. You are going to make your carbocation. Now that is the reactive species. And then if we've got water floating around, we're going to fill in that space. We are going to make rubbing alcohol. Do not forget that that is charged. This is not O minus. This is neutral. You have to have that extra step. I see that made as a mistake so often, and it drives me nuts. So don't make that mistake. Okay, again, we've got either water or Br minus floating around in here. Something is going to give that lone pair back. And you're going to form your alcohol. So we'll end up making your alcohol plus your HBr and water. Okay, if you didn't have a good Chem 2, these are the same thing. Okay, awesome, I love it. So I feel like we should stop here, and then we're gonna do one more video that gets a little bit deeper with the Sn1 E1. Of course, it's not just as straightforward. We have one more caveat to this. So let's stop this one. We kind of defined everything in here, and then let's make it just a little bit sassier in our next video.